Welcome back to the lectures in chemistry on the topic of atomic structure and chemical bonding. My name is Mangala Sundar and I am a professor of chemistry in the Department of Chemistry in Indian Institute of Technology, Madras, and you can see the email addresses here for you to contact. So, in this lecture, which we will continue from the previous matrix introduction and also properties of matrices, this lecture is on one of the important aspects in quantum mechanics, namely matrix eigenvalue eigenvector problem. The term eigen means characteristic. It is a property of the matrix. Eigenvalue eigenvector problem is fundamental in quantum mechanics in the sense that the Hamiltonian operator acting on the wave function, giving you the wave function back with a constant, which is the energy, the total energy. This is an eigenvalue equation for energy. Therefore, most of the solutions of quantum mechanics of real problems at some point of time or other will definitely involve solving them using computers and numerical methods, and for that process the matrix eigenvalue problem is one of the best known numerical techniques. Therefore, to understand the basic principles for this course and then use them to analyze the quantum mechanical properties and the measurements, etc., the concept of eigenvalues and eigenvectors is important. Okay. Now, before we do this, let me just recall with an elementary equation, a system of linear equations. Let me write down two simple equations. 4x plus 5y is equal to 0, and we have homogeneous equations. And then let me write another equation, 2x plus 3y is equal to 0. Let us assume that x and y are such that these two equations have to be solved. You will see that the first equation gives you 4x is equal to minus 5y, and therefore x is equal to minus 5 by 4 y. Now, if I substitute that x here, then what I get minus 5 by 2x, 5 by 2y, because x is minus 5 by 4 and 2x is minus 5 by 2y, plus 3y is equal to 0, which is essentially half y is equal to 0 or y is equal to 0. If y is 0, quite obviously x is 0. So, this is a trivial result, is not a solution. The reason that this system of equation does not have a non-zero or a non-trivial solution is that these two are both independent of each other, they are linearly independent. If you have two equations in two variables and both are linearly independent, the only solution that you have is that variables are 0. Therefore, it is important for these equations to be linearly dependent. And I am sure you have done this in your previous algebra, that the determinant of the coefficients which is written from this equation as 4, 5, 2, y, 2, 3, if you write this in the matrix form, this is what the equation is. The determinant of the coefficient matrix is the determinant 4, 5, 2, 3 is non-zero. It is 12 minus 10, which is 2, is equal to 2. Therefore, for a homogeneous system of coupled equations, the determinant, if it is not 0, such a system does not have a solution, a non-trivial solution, okay? And the trivial solutions are not relevant. So let me do the same thing now. If I look at the same equation, slightly different, let us assume that it is 2x plus 3y is equal to 0, and let us assume that 6x plus 9y is equal to 0. Okay. Now it is obvious by looking at it straight away that the second equation is 3 times the first equation, 2x plus 3y is equal to 0. Therefore, these equations are not linearly independent, they are linearly dependent. And you know, if you write the determinant, then it is 2, 3, 6, 9, that is equal to 0, because you know one row is nothing but the multiple of another row, and determinants, such determinants have 0 values. The moment you have this is actually one equation only, 2x plus 3y is equal to 0. Therefore, you have a solution x is equal to minus 3 by 2y. All it tells you is that x is in terms of y, but it does not tell you what are x and what x and y are. Therefore, one variable is undetermined or indeterminate. You have to give some number, and then you have to use x. If y is 5, x will be minus 15 by 2. But there is a solution. The solution is that unless y is 0, x is not 0. So this is a linear system of equations. Okay. Now homogeneous equations. If you have a system of inhomogeneous or non-homogeneous equations, you do not have a problem. You have to actually have the inverse of the matrix to be taken, non-homogeneous system. So let us do that. 2x plus 3y is equal to 5, and 4x plus it can't be 2x plus 3y and 4x plus 6y. Let us write 5y is equal to 4. Okay. Now these have a solution in the sense that this is a matrix equation 2, 3, 4, 5, x, y is equal to 5, 4, and therefore if you call this as a and you call this as phi is equal to some constant, then you only have to multiply this with an a inverse a phi is equal to c. Therefore, it is important for you to have an a inverse here, that is also a inverse. Okay. So a inverse is defined only if the determinant is non-zero. Therefore, you see this system of equations cannot have the determinant to be 0 if it is non-homogeneous. So these things are elementary algebraic equations and things you must remember. And now when we go to the eigenvalue eigenvector problem, we are generalizing this to a much larger and a specific type of systems, and the specific type of system is that if you have a matrix A and if you have a column something like xy, A being a 2 by 2 matrix. So let us write to this in terms of specific forms. Okay. A11, A12, A21, A22. The eigenvalue eigenvector problem is a specific set of equations which is a constant lambda times x and y. So what you have is, if you write to this as A and if you write this x as a column vector, xy as a column vector given by the operator by the vector x, and you write this as lambda x, then this is called an eigenvalue equation. And the eigenvalue equation is such that x is known as the eigenvector and lambda is known as the eigenvalue. Okay. So what you have is, you are trying to find out a solution x and y such that A acting on that solution gives you a constant times that solution itself. That is a very special case, and those special cases are most important in quantum mechanics, including the Hamiltonian equation. So let us do, in this case itself, let us try and find out what the eigenvalues are. Okay. Now please remember, if you expand this, A11x plus A12y is equal to lambda x. First row, you remember two matrices are equal only if the elements on both sides are corresponding elements are equal. So, the second one is A21x plus A22y is equal to lambda y, and therefore, you have A11 minus lambda x plus A12y is equal to 0, A21 plus A22 minus lambda, this is x and this is y, is equal to 0. Now, we are back to the homogeneous equation, and therefore, you see the reason for the previous analysis is that we used that right away, that we have to have the determinant of the coefficient matrix to be 0, which is A11 minus lambda, A12, A22, A21 and A22 minus lambda. This determinant should be 0 for this to have a non-trivial solution, x and y. That is, both x and y are not 0, that is what is non-trivial. Now, this is very easy, the determinant is easy to expand. So, you have A11 minus lambda times A22 minus lambda minus A12, A21 is equal to 0, which is now a quadratic equation in lambda. So, this is lambda square minus lambda times A11 plus A22, then plus you have A11 A22, okay, minus A12 A21, that is equal to 0. This is the standard form of Ax square plus Bx plus C. Therefore, the solution, you know, lambda can be written as minus B, where the coefficient is this one. Therefore, it is A11 plus A22 by 2 minus B by 2 plus or minus B square minus 4AC. If you remember, C is A is 1 and C is this. If you remember, Ax square plus Bx plus C is equal to 0, x is minus B by 2, A plus or minus square root of B square minus 4AC by 2. Okay. Keep that in mind, then you have the solution. Therefore, this is plus or minus square root of B square is A11 plus A22 whole square minus 4 A11 A22 plus 4 A12 A21. These are the two solutions with a plus or minus. Immediately you see that if, for example, we started with the matrix A11 with A12 being 0 and A21 being 0, if we started with a diagonal matrix, you knew that the diagonal elements are the eigenvalues, because if these two are 0, you can see that this goes to 0, this goes to 0, and therefore, this one is A11 minus A22 whole square, and the square root of this is going to give you A11 plus A22 1 by 2 plus or minus A11 minus A22 1 by 2, and the two solutions are A11 and A22. If these elements were 0, you are back to the original solution. But if these elements are not 0, which is what we are interested in, therefore, let me undo this highlight. Okay. For A12 A21, then the actual solution is what I have written down. So, there are two solutions, and therefore, there are two eigenvalues, namely lambda 1 is A11 plus A22 by 2 plus square root of A11 minus A22 whole square plus 4 A12 A21 1 by 2. Okay. And the other solution is lambda 2 is A11 plus A22 by 2 minus 1/2 square root of the same thing, A11 minus A22 whole square plus 4 A12 A21. Okay. So, these are the two eigenvalues. So, if we go back to the original matrix equation, we had A11, A12, A21, A22, x, y is equal to 0. now sorry is equal to now lambda 1 x y, and there is also another solution a11, a12, a21, a22. Now we may want to call it as x prime y prime lambda 2 x prime y prime, since lambda 1 and lambda 2 are not the same. Okay. And we will worry about what is known as a non-degenerate eigenvalue system. That is, the eigenvalues are all different, they are not equal to each other, or few of them equal to each other. All those cases we will not worry about it. Let us assume that the eigenvalues are different. Therefore, we have two solutions xy is one eigenvector associated with eigenvalue lambda 1. X prime y prime is another eigenvector associated with another eigenvalue lambda 2. So, a 2 by 2 system has two eigenvalues. In general, this is true that an n by n system has n possible eigenvalues, some of which may be equal to each other, the others, and it may also have a completely non-degenerate solution and so on. But this is what is the eigenvalue eigenvector problem. Now, having done this, what are the eigenvectors? How do we get x and y? How do we get them? X prime and y prime. Okay. So, quite obviously it says that a11 minus lambda 1 x plus a12 y is equal to 0. That is the first eigenvalue equation, and then the second row equation will be a21 x plus a22 minus lambda 1 y is equal to 0. It is not necessary for us to verify that the determinant is 0, because that is how we got the eigenvalues in the first place, okay, lambda 1, because the determinant is what we had it, a11 minus lambda 1, a12, a21, a22 minus lambda 1. This determinant is anyway 0, because lambda 1 is a solution of this equation. Therefore, we do not need to worry about it. Therefore, if you have to write it, you can write x is equal to minus a12 by a11 minus lambda 1 times y. The second solution is not independent of the first one. You do not need to solve the second equation. This is all you need to solve. Therefore, we know x in terms of y, and now you have to choose a y. Eigenvectors are always, or most of the time in linear algebra and also in quantum mechanics, are defined in such a way that if you have an eigenvector x, we use what are called normalized eigenvectors. The normalization, if x and y are real, the normalization essentially means x square plus y square is chosen to be 1. Therefore, no matter what I choose x or y to be, I have to set to the square of x and the square of y, the sum, to be 1, and therefore that constant goes away when you do that choice. We will see some numerical examples in the next session, and you see this requirement that the eigenfunctions be normalized removes the uncertainty or the indeterminacy of these variables, one of the variables x or y. It makes it very clear that x and y are proportional, and they also satisfy the second condition that x square plus y square is equal to 1. Therefore, x and y have very specific values. Therefore, the eigenvector is precisely defined, and it is defined as two different eigenvectors for two different eigenvalues. This is what I wanted to do. This is a very simple system 2 by 2, and let us stop here, and in the next part of it we will see some examples of doing this for the very elementary matrices that I have already introduced to you, the Pauli spin angular momentum matrices, the sigma x, sigma y and sigma z, and let us look at the eigenvalue properties as well as the eigenvectors and learn a little bit more, and also generalize this to other higher dimensions. Okay. Until then, Thank you. We will stop here for a break.